we didn't know it, of course, but the Germans were not really making progress on their construction of a reactor, but we had no way to know. And so people began to worry about even the dirty bomb. Even if the Germans do not succeed in building a reactor per se, they might be able to make radioactive materials they could then put in a bomb and drop on London. So that was one concern. And then another concern was back to the heavy water issue. Remember, this is the hydroelectric plant up in the mountains to the west of Oslo in Norway. And the Germans took Denmark without force and took Norway with some resistance around 1940 or 41. The Allies sabotaged this plant outside of Oslo. They snuck in a commando raid in February of 43 and blew up the 18 cells that were making hydrogen and for fertilizer purposes, but then also having heavy water produce D2O as a byproduct. And the Germans were interested in this. That's one way they took Norway, because they needed heavy water. They decided graphite would not work as the moderator for their reactor program. And so they needed heavy water. And they had no source of heavy water in Germany. And of course, once again, they decided that of course, we were working on two pathways in the U.S. to enrich uranium 235. That was Y12 at Oak Ridge, and also to make plutonium 239. In a reactor. And that was initially Oak Ridge, the graphite reactor, and then followed by Hanford, Washington, production reactor, or set of reactors. The Germans had decided they didn't have the resources or the material or the time to enrich uranium. And so Heisenberg had decided that instead, for their atomic bomb, they would have to build a reactor to make plutonium 239. And of course, our reactors use graphite as the moderator.
Touching an image causes it to fly into a neutron instrument chamber. The chamber door closes and moves into an SNS beamline on the next screen.
Yeah, somebody didn't mute their, somebody is out there in Etherland is watching the lecture, but didn't mute their computer, and they're doing two things at once. So that's what that was. Right. And so the other way, of course, is the German effort. Was to use heavy water as the moderator. And that's thus the German hydroelectric plant was, or the Norwegian plant was very important.
You selected the HIFER continuous neutron source. This screen asks you to choose the sample you want to study. At left are 3 rows, each with 2 categories of material samples from which to choose. Top row left, engineered materials. Image is a metal panel with a cutaway revealing inner structural elements. Top row right, biofuels. Image of 2 flasks containing water and green plant material. Middle row left, structural components. Image shows a suspension bridge, tower, and cables. Middle row right, 3D printing. Image is a 3D printed turbine rotor and the metal powder used to make it. Bottom row left, superconductors. Image is a piece of perovskite mineral. Bottom row right, batteries. image is a battery cell. Please select one category now.
Well, I don't know, we'll see. Okay. So even after the Brits and the Norwegian Underground sabotaged these 18 cells that was making heavy water, the Germans by fall had those cells working again. And so they were producing heavy water that they intended to take to Germany for their reactor project somewhere in Germany. The Brits tried to bomb that plant in November of '43. They dropped, they sent in more planes. They dropped bombs on the Molk plant, but that wiped out the power station, but didn't destroy the plant.
There's a movie made about that too. There was a movie made about that.
Two of them? Oh, I see.
Yeah, it's called 633 Squad.
Oh, I didn't know that.
It's Cliff Roberts.
Oh, can you write that down, Mary? Huh, I didn't know about that one. Cliff Robertson.
Yeah.
And what else was he famous for?
Playing
Right,
T-109.
PT 109, right. I did not know about that, Mark. Thank you.
633 Squad.
Oh, I had no idea.
You remember seeing that?
So the issue here was that the heavy water had been built up and the Germans wanted to move that, Nazis wanted to move that to Germany for their reactor project. The Norwegian intelligence got wind of this. They found out that the intent was to move heavy waters in February. The idea was to sabotage the shipment. They couldn't get into the plant to sabotage, so they were going to wait and until these 39 drums. Let me get rid of this here. So the idea was that there had to be a sabotage. There's 39 drums containing heavy water that would be taken out of this plant, loaded on a ferry, go across a lake in Norway, get to the Baltic Sea, go to mainland Germany for the reactor project. They found out the date of this. The underground in Norway learned that they'd be shipped to load on the ferry on February 20th. They decided they had to sabotage the ferry. The Germans, of course, were shipping this not on a separate boat, but on a passenger ferry, thinking that would help ensure that sabotage would not occur. The underground snuck on that ferry. The poor picture, but that's what it looks like, in the middle of the previous night, and planted explosives in the hold of the ship and used a crude alarm clock that would detonate the bomb, the explosives, when the boat got out to the deepest part of the lake. There were 53 passengers on board. The drums went by train, but they decided it was too hard to sabotage a train shipment. Too many explosives, too difficult, so they decided that sabotaging this ferry was the only way to effectively get rid of this shipment of heavy water to Germany. So they had the explosives on board. 45 minutes after the ferry left the dock, was out in the deepest part of the lake, then the timer went off and the explosives went off, tore a hole in the bottom of the boat, tilted the ferry so that the drums slid out of the hole of the ferry into that lake. And so they were destroyed, lost that way. There were people killed. Not everybody was crew killed, but there were 26 crew and passengers that died. And that was not the intent, but there was some concern about heavy water shipment to Germany that civilian casualties were thought necessary to get this done. We didn't know it then, but that was effectively the end of the German effort to build an atomic bomb. We do not know that they had rejected uranium enrichment as a pathway. We did not know that they had those technical difficulties. And so, but effectively, then in February 1944, that ended the German effort to build an atomic bomb. The Pacific War was continuing, of course, with full force. Most of our focus at that time was on the European war. That was closer to home. London was under attack. France, Netherlands, Belgium had been taken by Hitler. And so our focus was most on the European war. Of course, the fear was that Hitler would get to the atomic bomb before we did. That promoted great focus on that. The Japanese were an enemy of a different breed, was the feeling at that time. The Japanese were thought that they would never surrender. In fact, up to that time, the ratio of killed to captured was very high among the Japanese. The US military was used to a ratio of 4 to 1 of let's see, I gotta say that right. So ratio of captured to killed was always more captured than killed. And so you were used to, and standard battle times, to have a ratio of 4 to 1 of captured to killed. But I think I said that backwards, didn't I? 1 to 4. So there were 4 times as many killed as captured. And among the Japanese, in those campaigns against the Japanese, the ratio was more like 120 killed to captured. That's the point. So there were 3 times fewer captured.
Causes it to fly into a neutron instrument chamber. The chamber closes and moves into a Heifer beamline on the next screen.
Whoever's listening out there in Oak Ridge, you're sending us audio from a SNS. That's the only one I see signed up. Paul, are you there? If you are, please mute your computer because we're picking up transmission from your computer to our classroom. See, I don't know how to. Okay, is that me talking? Okay. Anyway, so we knew that the Japanese were an enemy of an entirely different type. And so Japanese rarely surrendered. This led in part to the decision by Churchill and Roosevelt that unconditional surrender would be necessary. We could see the end of the European War coming, and the invasion of Normandy was not far off, but the end of the Pacific War was a much more difficult concept. And so they were insisting on unconditional surrender. So let me go now to chapter 16. Well, there was a lot of collaboration by this time between the British and the American scientists in the Manhattan Project. In England, it was called the Maud Committee. There's a story behind that, but it's not really certain. And of course, they were ahead of us. Up until Pearl Harbor, the British were fully focused on the question of whether you could build an atomic bomb out of uranium fission. The U.S. was not. We were, our leaders, both the president, were trying to forget about that issue of whether to invest in that possibility. After Pearl Harbor, however, it changed. And By that time, then experts from England were telling us that we need to get involved and helping us along the way. Another thing, of course, in September 1941 was the visit of Werner Heisenberg to Copenhagen to visit his former mentor, Niels Bohr. And that's the subject of the play Copenhagen we'll start to watch next time. And Bohr's impression from Heisenberg is that Germans were making great progress on their atomic bomb project. Then Pearl Harbor occurred. Then August of 43, Churchill and Roosevelt met in Quebec and talked about details of tube alloys. That was the British code name for the uranium project. That was the device, tube alloys. Had nothing to do with the bomb, but they didn't want to say uranium. And they agreed that they were very worried about Germany's progress by this time. And so they agreed to send a group of British scientists to be part of the Manhattan Project. And so they started arriving in December of 1943, which is about the time that the graphite reactor at Ridge went critical for the first time. And Niels Bohr came. Niels Bohr got out of Denmark when the Nazis decided to go and collect up the Jews, the 8,000 Jews in Denmark. The tip came. Bohr's mother was Jewish. Bohr was about to be arrested. The tip came from the underground, and so Niels Bohr and his wife Margareta got over to Sweden. And then later, most of the Jews, 80%, 90% of the Jews, were hidden and taken across to neutral Sweden. So there's very little casualty of Danish Jews by the Gestapo. So Niels Bohr went to England, to Sweden, then New England, and then he came to the US in December of 43. His son Oa came with him. He has 3 sons. Oa was the physicist. I knew Oa before he died. He was head of the Niels Bohr Institute when I went there often over 30 years, from 68 onward. And so he was young then. He was his father's assistant. They came to Los Alamos. Of course, secrecy was important, so their nicknames were Uncle Nick and Jim. Not Niels and Oa, but Uncle Nick and Jim. And so they came to Los Alamos and shared with Oppenheimer and his team the idea of a reactor that Niels Bohr had picked up in his meeting with Heisenberg about 2 years before. And they showed the sketch. Niels Bohr came with this sketch. And it's just not understood where the sketch came from. Niels' son Oa maintains that Heisenberg did not leave a sketch of this rudimentary reactor with Bohr. Perhaps Niels Bohr sketched it out himself after his short but aborted meeting with Heisenberg in December 1941. But that's what he took with him to Los Alamos in December of 43 so that they could look at the German plans for a reactor. Well, that was a very important discussion, but the experts there was that this was not a real sketch. It was erroneous. Fermi had built a pile of uranium laced with graphite to make the first chain reaction. This was sheets of uranium rather than radiosphere, and their conclusion on Los Alamos is that this wouldn't work. This was crazy. You could not get a critical mass that way, and so it just wouldn't work. And of course, Niels Bohr was initially confused about whether Heisenberg was sketching out a bomb or a reactor. Bohr was a theorist, hadn't really thought much about the nature of a reactor that would go critical. And Bohr's real purpose, going to Los Alamos, was to get people in Los Alamos and our governments of England, United Kingdom, and US to start thinking about what happens after World War II concerning the proliferation of atomic bombs. And that was Niels Bohr's passion until he died in 1962, of trying to get the world to agree how to come to terms with a proliferation of atomic bombs. And, you know, once again, Bohr and Heisenberg were close. Bohr was 15 years older than Heisenberg. Bohr was his mentor before World War II. Bohr worked out the theory of the atom that required quantum concepts, quantum mechanics. Heisenberg was the superior mathematician that worked out the mathematical foundation of quantum mechanics that explained mathematically Bohr's intuitive views of how an atom at the microscopic level works differently than planets moving around the sun at the macroscopic level. So that's quantum mechanics. We got a Nobel Prize also. And Heisenberg often came to Copenhagen for scientific meetings. This is a photo of them in the lunchroom at Bladensweig. I've been in that room many times. Niels Bohr and his protege Heisenberg meeting before World War II. And but then they did have that ill-fated session in September '41, and that's what we'll think about when we watch the movie. And so that's the sketch that Niels Bohr took with him to Los Alamos to show people there where the Germans stood in their effort. And various people attended that meeting last day of December in '43, where Bohr could present this. Niels Bohr referred to this as the German bomb, but of course that's not a bomb, that's a reactor sketch. And Bohr initially did not realize the difference. And it was very inefficient. You could never build a reactor with sheets of deuterium oxide, sheets of uranium interlaced with heavy water. There's the heavy water, U2O. That's what the Germans needed from Norway. So it was a vat of heavy water with sheets of uranium metal or uranium oxide in between. And people in Los Alamos realized that wouldn't work. You never get a critical mass by having the pieces of the uranium pile distributed that way. And so there was debate about whether Heisenberg had really shown that to Bohr, sketched that to Bohr, whether he had done it from memory. And then there was debate about what was Heisenberg's intent. Was Heisenberg trying to deceive Bohr, showing him an erroneous sketch that wouldn't work? Heisenberg was maybe telling Bohr that that was their direction, to build a plutonium bomb with a reactor. And so, you know, maybe it was 2 years. It was 2 years after that fateful meeting, and maybe Bohr had just forgotten about the details and sketched that drawing later. So it probably was all kind of a mistake, or was it Heisenberg's intent to give Bohr the signal that they could build a reactor, and perhaps that they wanted to, perhaps Heisenberg wanted to tell Bohr that he had control of the German atomic bomb project, to impress Bohr that they had a sketch of a reactor on the way, and that they wanted to he wanted to tell Bohr that he could, if Bohr could stop the Allied effort, Heisenberg could stop the German effort. That's still not known. It's not known then whether Heisenberg really did sketch it out for Bohr and what was his intent, whether he did or not. So it's all very confused with the history of that. On that trip to the US, late '43, early '44, Bohr met with Felix Frankfurter. Felix Frankfurter was put on the Supreme Court by President Roosevelt in 1939. He was Jewish. He was born in Vienna of Jewish parents who came to the U.S. when he was 12, when Felix was 12. They were generally rabbis among his ancestors. Felix went to Harvard Law School, was brilliant. He then worked for Harry Stimson when Harry Stimson was in New York. And then Harry Stimson became Secretary of the War. Felix Frankfurter was a Harvard faculty member in the School of Law, and Roosevelt appointed him to the Supreme Court in 1939. Bohr met Frankfurter already in 1933, probably because of his efforts to help Jewish scientists get out of Germany, get to Denmark or the UK or to the US. And so Bohr visited Frankfurter in 1939 and became good friends. Frankfurter was close to the president after he was appointed to the Supreme Court, and an amazing chain of events happened as Bohr pushed his ideas, his fears of post-World War II control of atomic weapons, atomic bombs. And it's really surprising that a physicist actually met with the President of the US and Prime Minister of the United Kingdom over these issues of what happens after World War II in a world of proliferating atomic bombs. Frankfurter knew something about this secret project, though not much. He did not know the details. He was on the Supreme Court, did not know the details at all of the Manhattan Project, but he knew something was going on. He called it Project X. So when Bohr met with him in February of 1944, they talked around the topic. Bohr, of course, had just been to Los Alamos. He knew quite a bit about the Manhattan Project. Frankfurter knew vaguely about it, and so they talked obliquely about Project X, never discussing what it was or the details of it. But Frankfurter seemed to agree with Bohr that what happens after World War II, if the US and the UK can build an atomic bomb, Germany's probably doing the same. What happens to the rest of the world? And so Frankfurter agreed with Bohr's concern over a post-World War II world of atomic weapons and agreed to take those concerns to the president. Frankfurter did talk to Roosevelt about that, and Roosevelt agreed that he was concerned too about what happens after the war ends. And he suggested that Bohr should express the president's concern to British authorities. See, Bohr was sent partially by Sir John Anderson, the head of one of the leaders of Churchill's government, sent Bohr in part to ask that question, promote that concern that Anderson had about proliferation of atomic weapons after World War II. And so Roosevelt suggested that Bohr take his concern back to the leaders of the British government. You know, he didn't want to undercut Churchill, but he wanted Bohr to just explore the depth of the concerns in the British government about post-World War II weapons. You know, and Bohr considered this another example of complementarity. In physics, Bohr pushed the idea of complementarity, that you could view physical phenomena in complementary ways. Light, for example, is usually viewed as a wave, but you can also view it as photons, packets of energy like particles. And you know, Einstein explained the photoelectric effect in 1905 by assuming that light was a packet of particles. And electrons you could view as particles moving around the nucleus, or you could view it as waves also, depending upon the way you're observing them and the phenomenon that you're explaining. So that's complementarity in physics. Things have complementary views, wave or particle, for example, depending upon how you measure them and how you look at them. Well, Bohr applied that same principle to atomic weapons, that atomic weapons are a threat, but also an opportunity. A threat because you could destroy the Earth. If you let development of nuclear weapons become widespread with every country having them, potential to destroy the Earth would be great. However, there would be an opportunity, a complementary advantage of that is a way for nations to agree to avoid mutual destruction by agreeing to control nuclear weapons, and maybe even to start discussions about the issues that different countries have. So the awful nature of nuclear weapons would perhaps promote a discussion among countries that would lead to solving some of the problems of poverty or inequities or liberty or whatever. And so you view that as a complementary type of issues. And the idea came that, you might have, even though nuclear weapons were and would be even more awful, it might lead to a way to have peace on Earth because no one wanted to destroy the Earth by launching nuclear bombs at each other. And so that was what he was pushing. And so the communication between nations was important about this problem. That may lead to more openness among nations, might lead to kind of a utopian view, peace and prosperity among all nations. The first step in this openness, Bohr said, was to give the secrets on the atomic bomb to the Soviet Union. The Soviets were our allies against Hitler. No one expected that to continue after World War II. And so the first step of the openness would be to give the secrets of how to build an atomic bomb to the Soviets so that they would cooperate with us and with England after the war to control nuclear weapons. So Bohr went back to England, and with the idea that he had a signal from Roosevelt through Felix Frankfurter to maybe he should propose to the UK leadership and a perspective of openness on nuclear weapons, not secrecy.
Was
Yeah.
any of such talk also coming from from Oppenheimer and that group toward Roosevelt?
Not at that time.
Not at that time.
No. People were concerned about that. Szilard, of course, was always of that mind. Science should be open. Secrets should be open. That the best way to do this is to be open with other countries. But by and large, people, Los Alamos, were pretty intent on beating the Germans to the punch. That was the overriding concern. So Bohr did go see Sir John Anderson when he got back to England, and said he had a signal from Roosevelt that Roosevelt was concerned about this. Anderson sent a message to Churchill that Churchill should hear Bohr out. And so Anderson and Churchill and Bohr met in May of '44. Well, that meeting crashed and burned big time. Complete disaster. Churchill was in a bad mood. They're preparing for the invasion of Normandy, June 6th of 1944. Churchill didn't want to waste his time talking to a nuclear physicist about esoteric things like openness of nuclear weapons after World War II. He cut Bohr off, did not let Bohr, who was soft-spoken and kind of wandering in his speech pattern, cut him off, didn't let him finish his presentation, didn't like this scientist trying to interfere in affairs of government. He said that he and Roosevelt could handle this on their own. They didn't need Bohr interfering with this. And he sure as heck didn't want to release the secrets of the atomic bomb to the Soviets. So the meeting crashed and burned. Churchill was very angry at his Chancellor of the Exchequer for setting this up. It was a complete disaster. Well, this is, of course, what Churchill was preoccupied by. June 6, 1944, the invasion occurred of Europe, continental Europe, the biggest invasion in history.
And of course, we'll go into details on that right now, but the Germans were fearing an invasion. There was what was the name of it? Calais, I guess. There was a port, a deep sea port out here at the tip of Normandy, and everybody assumed the invasion would occur there. But Eisenhower's plan was to invade Normandy here. And that was difficult because there was no deep sea port. So part of that was the invasion was to bring over old ships that could sink to make an artificial breaker, an artificial port, artificial harbor to which you could dock the invading warships. So the Germans were caught by surprise. They were fortified out here. They were not expecting an invasion here. And there's a long history of D-Day, but it worked.
The Germans were caught by surprise, and that was the beginning of the end for Germany. Of course, it took another 9 months before the surrender occurred, but that was a huge step in the European war. War went back to the U.S. He was focused on this issue of post-war openness about nuclear weapons. Ford told Frankfurter later in June about the disastrous meeting with Churchill. Frankfurter agreed to get an audience of Bohr with the president. Remarkable. And so that happened in August, not till August. Bohr and Niels and Owen Bohr hung around the U.S. a very hot, steamy summer. They spent a lot of their time in D.C. Of course, this was well before air conditioning. Very hot summer, typing and retyping a letter before they went to see the president of Bohr's views. And Owen Bohr acted as his father's secretary, he was the typist. They met with the president in August. Roosevelt was cordial, and he agreed that an early approach to the Soviets after World War II might be a good thing to try to cut off an arms race where the Soviets were trying to catch up and overtake the U.S. and the UK. Roosevelt knew that it was not surprising that Churchill was opposed to this idea of giving the secrets to the Soviets, but he knew that Churchill was initially opposed to ideas that he eventually came around to. And so he left the impression with Bohr that he would bring this up with Churchill in a meeting soon thereafter. That meeting occurred then in September. They met at Hyde Park, Roosevelt's estate, upstate New York, up the Hudson River. And Roosevelt quickly yielded to Churchill in his opposition to Bohr's ideas. And after that meeting between Roosevelt and Churchill, Churchill wrote down what they agreed to, the president and the prime minister. They agreed that they would reject the idea of informing other nations, including the Soviet Union, about the secrets, the details of atomic weapons. That U.S. and UK would continue to cooperate on the development after the war, on development of nuclear weapons and nuclear energy. Also, Churchill wrote down that Bohr should be watched. He might be a spy for the Germans. Maybe even Bohr should be detained because he was so adamant in these ideas that Churchill didn't trust him and thought he should be arrested. Well, advisors to Roosevelt and to Churchill interceded on Bohr's behalf, so he was never put under surveillance, much less arrested. But one clear outcome is an overture to the Soviets was dead in the water, And that's what Ford was pushing big time. Things were moving fast at Los Alamos. Hans Bethe had come to the US from Germany, came to Los Alamos. He was appointed head of the theoretical division. You know, Edward Teller was not appointed head of the theory division. Teller was one of the Hungarian Jews, very smart, but thought he should be head of the theoretical division of Los Alamos. But things were moving fast. When they were starting to design the atomic weapon now, assuming that you get enriched uranium from Oak Ridge or plutonium from Hanford. So the design was continuing. Segre was one of Fermi's sidekicks in Rome, who is now working the Manhattan Project, and he had measured in Berkeley spontaneous fission rate of uranium-235, and that was an important issue. You see, uranium-235 has a half-life of 0.7 billion years, and it of course will fission when you hit it with a neutron. But if you just have it sitting there on its own, it does have radioactive decay, that half-life. And the way it decays is by emitting an alpha particle, thorium. This whole chain of radioactivities, all these are radioactive elements, all long-lived. Most of them long-lived. And eventually you see that chain of decay, you get down to something stable, about 207. So that people knew about. But also, turns out that uranium-235 will fission on its own. It's not very common, but that's called spontaneous fission, where even if you don't have a source of neutrons, a chain reaction, uranium-235 on its own might undergo spontaneous fission decay. And a concern was how bad that would be. And Segre had measured the rate of that while at Berkeley, and the number was too high. And that meant that you had to have twice the material of enriched uranium-235 than you might have thought, and the uranium bomb was going to be big, 17 feet long, because you had to have, because that spontaneous fission decay, you had to shoot part of the uranium into the other very fast, and you had to have a lot of material there. But when Segre got to Los Alamos, he realized that the spontaneous fission rate was not nearly as high at Berkeley as he had measured at Berkeley. In fact, it was only 2 out of 10 to the -7th of the alpha decay. Very rare, but still present. But he had measured 100 times larger the rate at when he was at Berkeley, probably because of he was getting cosmic rays or something, making neutrons, causing uranium to fission, and he was deceived by that. But when he got to Los Alamos, he did a better measurement and realized that number was awfully small, which was good, which meant that Thin Man would become Little Boy. You only needed a bomb that was 6 feet long, more easily loaded than an aircraft. If you could develop it, you could then use on Japan. So that was a good sign. Now, the real problem with Los Alamos was making the plutonium bomb. Still didn't know if you get enough uranium-235 from Y-12. Ray Smith talked last time about how in late 43, all the Calutrons weren't working. They had to send the tanks back to Milwaukee. They were behind schedule. And so at that time, the focus was on using plutonium to make a bomb, coming out of the production reactors at Hanford, which were being built at this time. That had to be an implosion device because of this spontaneous fission element. You have to make it happen quickly. And Seth Niedermeyer was a physicist that was head of that implosion effort to figure out how you take a spherical array and make it suddenly explode symmetrically and compress the plutonium down very quickly. And so there were a lot of tension over how to do that. See, the issue was it had to happen fast. You had your plutonium in the core. You had a little source of neutrons in the middle, a polonium source hitting a beryllium foil to make a few neutrons. But to make a critical mass, you had to symmetrically compress that plutonium quickly. And so you'd have some tampered material, and then you have some spherical array of explosives. How do you get those explosives to all go off in a very symmetric way to completely symmetrically compress the plutonium down to a critical mass? A huge technical problem. And so there were problems getting that done. There were personality problems. That Seth Niedermeyer was head of the project, but they were having of the implosion project, but he was not a good leader, and they were getting nowhere on that. And this was a critical pathway, so Oppenheimer knew that he needed more help. And so Conant, one of the leaders, the head of Harvard, called on an old Harvard faculty friend, George Kistakowski, who came from Ukraine to the US, a chemist. So he was called into Los Alamos. He was the guy that did the analysis for Conant 2 years before, saying, yeah, this might actually work. You better take notice of this, James Conant. And that guy Conant really inspired to support the idea of a Manhattan Project. So he asked his friend Kistakowski to come to Los Alamos to work on this. Niedermeyer, a physicist, reported to a captain. They didn't get along at all. They were head of the implosion project. Nothing was working right. Neither of them wanted Kistakowski, the Harvard professor, to come in and take charge of this. So Oppenheimer had a huge human resources problem, personnel problem, but he had to get this done. Another character in this story was Stanislaus Ulam, a Polish Jew who got out of Poland before Hitler took Poland. And Ulam was on the faculty at University of Wisconsin, and he was sent to Los Alamos. He was a mathematician to work initially with Teller on the superbomb, but then he also was brought into Beta's theory division to help on implosion because Niedermeyer's group wasn't getting it done. Kistakowski was called in from Harvard to work on this huge implosion problem. So also von Neumann was brought in, another Hungarian Jew, one of the great mathematicians in the history of mathematics, sort of father of the computer. He was brought in too to help Ulam on calculations of how to make this implosion completely symmetric, how to do it. Also, there was the first computer. It was called IBM Punch Card Sorter. Was the first device. Instead of doing these calculations by hand with a slide rule, very complicated calculations of a spherical array of explosives, they had some kind of an early stage computer to help them on this brute force calculation. Von Neumann was an expert on that, and he helped build that first crude computer. And so that was a crucial contribution that von Neumann made. Also, British efforts came. After Churchill and Roosevelt met in Quebec in August of '43, Churchill sent some British scientists over to help on the Manhattan Project on this implosion problem. James Tuck had worked on designing and shaped charges, conventional TNT explosives for penetrating tank walls to get more bang for the buck. Tuck suggested that you should take a different approach, that you needed converging waves, shock waves from each of the many different explosives converging on the tamper. Previously they tried to smooth out the collection of shock waves from the various explosives to make them be uniform, but that wasn't working. So it's a subtlety I can't really explain in detail, but James Tuck and then Jeffrey Taylor arrived also from England and then demonstrated mathematically that what you needed to do is have a explosion device with polygonal lenses around, so that would produce a spherical shock wave, so that when the core got compressed, it would be done in a completely symmetric way, a converging way rather than diverging shock waves. That's a little hard to explain, but that was the direction they took. And so Taylor and Tuck brought that idea that you had to have depend on the tamper and on the explosives. And so some way, if they could do that in a different way, they would be able to make a spherical shock wave occur. Taylor was moved out of the way by Oppenheimer, put him in charge of the super bomb, the fusion bomb, because he refused to work on this implosion problem because he was not appointed head of the theoretical division at Los Alamos. Also, they brought in Rudolph Pears from England to help on this implosion process. Back to Oak Ridge. If you're going to get to the Hanford and build production reactors at Hanford, you need to make the reactor in Oak Ridge work. Fermi was there in Oak Ridge to try to make this work. That's what we'll show you in November, the graphite reactor. At Oak Ridge, it was a massive block of graphite, the moderator for the neutrons, surrounded by a shell 7 foot of concrete, and there were 1,200 tubes, holes going through the graphite into which you would put tubes of uranium metal or uranium oxide. Some of the tubes were left open for air circulation to cool the reactor. So it was an air-cooled reactor. Compton and Fermi were there in November of 1943 when the pile first went critical. That was, they scaled up Fermi's CP1 under the football stands at the University of Chicago. We figured out how big it had to be, how many rods of uranium you needed, how much graphite you needed. And so they started to produce. The reactor went critical in November of 43, and then they figured out how to do the radiochemistry, so they started to produce small amounts of plutonium. They worked out the radiochemistry of that, and so they were making milligram quantities of plutonium, as Ray described last time. Those were then taken by courier, personal carrier on trains to Los Alamos, so that people at Los Alamos could start to experiment with how to handle plutonium, and eventually you got kilogram quantities, making it into a ball. However, they were surprised when they started to get quantities of plutonium at Los Alamos. The spontaneous fission rate was large. With the reactor produced quantities of plutonium-239.
So you see it was small for uranium-235. You probably figured out. Which enabled Little Boy to be a decently sized bomb. But the surprise here, when they started to get small quantities of plutonium-239 from Oak Ridge, it has a large spontaneous fission rate. Now, is it would fission on its own? Well, the difference, that had not been measured at Berkeley when they made plutonium in an accelerator in the cyclotron, but the difference here in a reactor, it was actually plutonium-240 that had the high spontaneous fission rate. Because in a reactor, you can make plutonium-239, but then you could also capture a neutron, another neutron in this environment, to make plutonium-240. It turns out we now know that plutonium-240 has a high, rather high spontaneous fission rate, and that's a contaminant in the plutonium that you produce in a reactor, and that's what drove the implosion project. The importance of that, because that would tend to make the plutonium bomb fizzle. And so when this was observed, that's when they had to really focus on making an implosion device for a plutonium bomb. There's no way to purify plutonium in mass 239, get rid of the mass 240. No technical way to do that at that time. You must live with that contamination. And so you got to make it work fast. If you had a slow gun type process like the uranium bomb, where you shoot the uranium bomb, you've got a hunk of uranium-235. You have an anti-bomb in. If you have an annulus, you shoot it with TNT down, and when that cylinder, that color of uranium becomes clear, you've got a critical mass, and you have the chain reaction, and the device blows. That would be too slow, because uranium-240 would start to do spontaneous fission. It would make that moving collar of mass fizzle and go off before it got coincident with the critical mass. And so you would need a very high muzzle velocity to achieve that. It just was not achievable. And that's what led to the idea that you had to have an implosion device for plutonium, which is much more complicated. And so he brought in a lot of resources. You know, he had to ignore the bruised personalities of Niedermeyer, the physicist, and Parsons, the captain. He formed 2 new research divisions working on implosion. This is a critical pathway. He put Kistikowski, the Harvard professor, in charge. He brought in more people. The number of people working at Los Alamos was up to 1,200, scientists and engineers and chemists, physicists, and that would redouble again. So more and more resources were putting into many aspects, especially implosion, so that the plutonium bomb would work. This was not going well. You know, the problem in this pathway was, could you make an implosion bomb work? The problem in this pathway was that the calutrons weren't working. As we discussed last time, you know, the coils were designed wrong, the oil was dirty, used to cool the coil, making magnetic fields in the calutrons. And so by spring of 44, no enrichment strategy was working. And gaseous diffusion was a possibility besides uranium enrichment, K25, another way to enrich uranium at mass 235, that needed a barrier, as Ray described, a little foil with thousands of pinholes per square inch, so that uranium 235 hexafluoride and uranium 238 hexafluoride would diffuse through those pinholes at different rates. And so that's what K25 was going to be, a huge consecutive set of barriers that would step by step enrich uranium in mass 235. But the barrier was difficult to fabricate. So that was not working well. Out of desperation, they started the S50 thermal diffusion project. A guy was working on this, Philip Abelson, relative to reactors for ships. They felt that that could give a small enrichment of uranium-235 because of thermal processes, where you would have uranium hexafluoride heated up, and it would diffuse differently to a cold wall based upon the molecular velocity of different velocities of uranium hexafluoride with either 235 or 238. And so General Groves quickly put up resources to design near at K25 across the street, S50, a thermal diffusion plant that had 2,100 of these columns to try in a desperate way to find a way to enrich uranium in 235. And of course, Mark Miller said last time that when you came to K25, your lab was in that power plant, right? Yes. So this is another desperate way to try to get enrichment going because things were not working well. And so that was these very tall tubes. Until was built 2,000 of these, where you would have this thermal diffusion, uranium hexafluoride separated because of different molecular velocities, because of the different masses of 235 and 238 uranium hexafluoride. This was continued, and then the idea the Groves had was to try and feed this slightly enriched uranium then into the beta calutrons at Y12 once they got running. In the Pacific, summer 44, D-Day had occurred June 6th of 1944, where the invasion of Europe started. In the Pacific, the U.S. was recovering from Pearl Harbor. The Japanese had taken a lot of the islands. Their intent was to take Hawaii at some point, but then they got beat. The U.S. beat them at Marshall Islands and Guadalcanal. So by summer of 1944, the U.S. wanted to take Saipan and Tinian for a base for the large new super fortresses, the B-29s, that would start dropping bombs on Japan. There had been the surprise Jimmy Doolittle attack on Japan earlier to show that were possible, but now the next step is to have a large new fleet of super fortresses carrying more bombs as you could attack Japan. U.S. invaded Saipan on June 15th. In July, they invaded Tinian. Both worked. Bloody battles as they got closer to Japan. Here's Saipan and Tinian. So they were progressing closer to Japan. They also realized, of course, that on Saipan, when the U.S. succeeded in taking that rocky island, it was a difficult battle.
there were 20,000 Japanese civilians that jumped off a cliff together after the U.S. took that island. Once again, the idea of surrender was not in the Japanese culture. And if you lost the battle, you committed harikari, basically. And so 22,000, more or less at one time, did a mass suicide jumping off a cliff in Saipan rather than being taken by the Americans. And that led to this idea that invading Japan was going to be much worse than invading Europe. So, here's Saipan. People were progressing, trying to get closer to Japan. Reactors did start to run at Hanford, Washington. And, Hanford was chosen from other sites being considered for the production reactors. Graphite reactor was in Oak Ridge. The purpose of that was to demonstrate you could build a reactor. Then Rose did not want to build the larger production reactors in Oak Ridge because it's too close to Knoxville, civilian population. So the Northwest was chosen. They had the Columbia River, a good source of water for cooling, good source of electricity by hydro, maybe building dams. We had Grand Coulee Dam, Bonneville Dam, that gave a whole lot of electrical power to build these reactor facilities at Hampton, Washington. It also could be, remote. We had a lot of land, it was rather desolate. And so they started construction of 3 production reactors. It all happened very quickly. The decision was to water cool those reactors. They were not a megawatt, but 250 megawatts. Air cooling would not work. Helium cooling was viewed as too difficult in a short time. And so water from the Columbia River was used to go through many little empty channels, similar to a graphite reactor, but bigger, to start to build these reactors. So the first reactor went critical in September of 1944. This is less than 1 year after the graphite reactor went critical in Oak Ridge, so things were moving very rapidly. Scaled up version of the Oak Ridge reactor. The pile went critical in September. Fermi was there to insert the first uranium slug. And the problem they had, though, was this was all new territory. When they loaded up all the uranium slugs, you had the water flowing to be a coolant. You had the graphite as moderator. It would run for a while, then it would stop. You lose the criticality, the chain reaction. Well, John Wheeler, when Princeton happened to be there at Hanford, he figured out the problem. The problem was, he finally figured it out by looking at how long the reactor would run before it would shut down. Based the half-life of that one fission product, the uranium fission is iodine 135, has a half-life of 6.6 hours. The problem is it beta decays to xenon 135. Turns out that has a large neutron capture cross-section. That's why after 6 or 7 hours, the reactor stopped working, because you made iodine by uranium fission. If you came with a half-life of xenon, once you got enough xenon built up, that sucked up neutrons, and the chain reaction stopped. Big problem. Luckily, they had built the matrix big enough, and Wheeler helped figure out there was just a case of this poison being built up, and to counter that, you just had to put in more uranium slugs to get more than enough neutrons, so that even if you have this poison being built up by radioactive decay, you would have enough fission. And so they added 500 new slugs in the corners, and that was enough to overcome the nature of this xenon poison that you build up naturally. And then the Hanford reactors could start operating in a continuous manner. And Groves, for the first time, was now optimistic, once the 3 Hanford reactors started running, that he could make enough plutonium, maybe even to have 18 5-kilogram plutonium bombs by the second half of 1945. So for the first time, there was optimism. You know, this was still in question, but now the Hanford reactor seemed to be running. And so Groves was, for the first time, optimistic that you could get a whole passel of plutonium bombs by late in 1945. Well, that was a little overly optimistic, but it turned out that that was the right direction. And so it was a constant seesaw of optimism and pessimism, whether this would all work. Okay.